Hi, folks. Welcome back to Physics with Captain Rod. I just wanted to start that one out with a little jingle there. What we're going to talk about here, we're going to talk about the inverse square law for radiation. Inverse square law for solar radiation. Not just solar radiation, actually all radiation. Any radiation that's coming from what's called a point source. So imagine here we got this light bulb, and in this example we're going to imagine this is a 100 watt bulb. So we'd say that its power is 100 watts. And a light bulb pretty much gives up radiation in all directions pretty much uniformly. So I'm going to do is I'm going to draw these little squigglies here to kind of represent radiation coming from the bulb in all directions. Right? And how bright the bulb is depends on where we're observing from. So I'm going to let this eyeball, like right here, represent my observation point. In the beginning of this example here, we're going to imagine that this is a distance of 2 meters away. And what we're going to do is we're going to calculate a quantity called intensity, which is power per unit area. Now, I'll start this by drawing an imaginary sphere here. I'm going to center it on the bulb. And imagine this imaginary spherical surface here that has a radius of 2 meters. I'm actually going to draw this radius in here. All right. What's important to realize is that all 100 watts is going to go through that spherical surface. And it's also very important to realize it's a three-dimensional surface I'm drawing. So it's, kind of looks like this, and it's got a backside as well. All 100 watts are going to go through that surface. If I were to calculate the intensity, is going to equal power, and again, because all the energy from the bulb is going through the surface of the sphere, then the power is going to be all 100 watts divided by the surface area of that sphere. Now the surface area of a spherical, the surface area of a sphere is 4 pi times the radius squared. In this case, the radius is 2 meters, and that's being squared. Now if I go through and calculate a value, this comes to be, I think, about 1.99 something. I'm just going to call that approximately 2 watts per square meter. Right now, that 2 watts per square meter would be good. That number would be good whether my eyeball was here or over here or maybe here or anywhere on the surface. And again, it's a three-dimensional surface. You've got to imagine like almost a volleyball looking thing here. Right. Now I'm going to do another calculation. I'm going to imagine we move out here a distance of 4 meters away. Right, so this is supposed to represent an eyeball, or we'll just say an observation point. If I were to calculate the intensity now, well, the first thing you need to realize is if I drew another spherical surface around this, let's see if I can do that here. Take my original sphere and make it larger. Yeah, I can do that. Okay, so if we draw another spherical surface, it's extremely important to realize that all 100 watts go through the second surface as well. So the power up top here is still 100 watts. What's changing is the bottom, the area here. So this is going to be 4 pi times 4 meters squared. And if we go ahead and calculate a value now, we get 0.5 watts per square meter. So you'll notice that if we when we doubled the radius, when we went from 2 meters to 4 meters, and again in that second example this was supposed to be 4 meters, that the power was cut by a factor of 4. Had we tripled the radius, meaning we go to an 8, the power will be cut by a factor of 9. And the reason is this: because intensity is power over area, and the area is equal to r squared. If we double r squared, you get, the bottom ends up being 4 times as large. And if we triple r, we end up making the bottom 9 times as large, because if you take 3r and you square it, the r squared factor is 9 times as large, and so forth. Now also notice that if I take the power and I divide by this 4 pi, I'm getting some numerical constant. So another way to write the intensity intensity can be written as some constant over r squared. And this would be true really for any radiation source that's a point source, meaning that all the radiation is coming from a point, as long as it has spherical symmetry. Now, in a lot of types of problems, we know an intensity at some point, and we know a radius at some point. So what I can do here is I can take this equation and I can put like ones on it. Maybe call this I1 and R1. And now imagine the radius changes to some other value, which I'll call maybe R2. If the radius gets smaller, meaning if our spheres are smaller, the intensity is going to go up. If the radius gets larger, the intensity is going to go down. Either way, I can write a new equation that says I2, the new intensity, is a constant over R2 squared. And what's extremely important to realize is that these constants are the same. If I wanted to, I can combine these two equations into one. And the way, one way to do that, if I take this equation and I solve for the constant, it's equal to I1 times R1 squared. And then if I solve for this constant, you'd have to multiply both sides by R2. The constant would equal I2, whatever that is, times R2 squared. And because the constants are equal in both cases, oops, not what I wanted to do, then we can say that I1 R1 squared is equal to I2 R2 squared. Right. So what I'm going to do here, I think I'm going to stop this video in a few minutes and just draw, make another video for my examples. But what I want to talk about, just kind of an overview here, is how intensity is calculated. It's power per unit area. Given the power of the source and a distance, we can calculate the intensity fairly easily. The area will be a 4 pi r squared term if we're talking about a spherically symmetrical problem. I can also relate that intensity to the intensity at some other distance by writing out the intensity equation again and basically just solving for the constant and eliminating the variables. So that's going to give us this relationship. So basically, if you tell me an I1 and an R1 and then give me an R2, I can tell you an I2. Keep in mind that when R2 gets bigger, the intensity falls off, and when when the R gets smaller, the intensity will go up. And it's also important to qualitatively understand by what type of factors, right? So for example, if we were to again double the radius from 5 meters to 10 meters, the intensity is going to fall off by a factor of 4 because of this R squared term in the bottom. If we were to triple the radius, the intensity will change by a factor of 9 and so forth. And going the other way, if I were to cut the radius in half, meaning I go from 2 meter to 1 meter, the intensity will increase by a factor of 4. And if I were to cut the radius by 1/3, the intensity will increase by a factor of 9 and so forth. So that's kind of an overview into the inverse square law. And I guess to say, what is the inverse square law? This right here. The intensity of any sort of light source, as long as it's what's called a point source, meaning all the light's basically coming from a point, that's going to give us a spherical symmetry. And then the intensity is directly proportional to 1 over r squared, or in math we would also say inversely proportional to r squared, meaning equals some constant over r squared. This is the inverse square law. It can be written, in different ways. This would be another way of basically writing the same law. So I think I'll just save the examples for another video. I hope this helps describe what the inverse square law is. Have a great day.